Okay, hello everybody. My name is Kogan. I'm an artist and a programmer. I hope all of you can hear me. I'm just looking at a screen right now. It's not what I'm used to. Usually these are in person, so hopefully this is all working okay. I'm going to take you through some work that I've been doing on the sort of more aesthetic side of machine learning. And this is called the neural aesthetic, obviously referencing neural networks. And first of all, I'm just very honored to be part of this conference. There's a lot of really amazing names on it. I'm sure lots of you are already quite familiar with some of the more academic and technical and scientific aspects of machine learning. So I'm going to show you a little bit of what maybe you don't get to see just quite as much of. So without further ado, I'm going to share my screen and go into my slides. So, okay, screen on, and great. Okay, so just to start, most of what I'll be showing is kind of scattered about these websites, and I'm going to take you through, if I have time, in just a little bit. I make a big habit of sharing everything as I go, so you can kind of find this stuff online in these places, and I'll kind of return to this in just a little bit. Just a little bit about me. Turn the audio down. I have a sort of a hybrid practice, so I've been researching machine learning for as a sort of applied machine learning research in several capacities, mostly with music information retrieval. This is sort of my start into machine learning. This is a field that probably some of you are familiar with. And I'm also a practicing media artist. I work with interactive installations and performances and video and sound and things like that. And I'm always kind of informing one practice with the other. So I'm trying to kind of bring what I understand about machine learning and AI and data science and all this kind of stuff into my media art practice, and vice versa. I'm trying to kind of bring what I understand about the way people like to engage with technology into how I work with machine learning. So that's a bit about my background. Almost everything that I'll be showing you today are applications of convolutional neural networks. So I'm sure lots of you are probably tired of seeing diagrams of circles with connections between them. So I thought maybe I would spice it up with this picture of this rainbow by neuroscientist Katie Matha that I found online. This is actually and I don't want to overstate the analogy too much because, of course, neuroscience and machine learning are really fields apart by now. But really, there's kind of this interesting interlap that neural networks were obviously inspired a lot by brain science, even if they're not really actually actively using it anymore. But there's really something really interesting and beautiful inside neural networks and obviously real ones as well. So I'm going to quickly describe convolutional neural networks. But first, sorry, I'll just, these slides are probably out of order. I just want to say, like, there's a lot of hype growing around machine learning and neural networks, and it's not new. I just want to share this, this amusing front page article, not front page, but this article from the New York Times from 1958, when the first perceptrons became very useful. And I really love this. It says, new Navy device learns by doing. Psychologist shows embryo of computer designed to read and grow wiser. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So I just want to say, the more things change, the more they stay the same, so to speak. We see neural networks are everywhere. They've been involved in a lot of obviously self-driving cars, and computer vision applications are using them a lot. But they're also in lesser known areas. So they were at the heart of the AlphaGo series, where Google's DeepMind trained an AI to beat the world's top-ranked player in Go. Deep Dream is obviously another one that I'll kind of get into later. And they're also used a lot in audio processing. So they're really quite everywhere. And I'm going to show you quickly a little bit about how they work. So lots of you are probably familiar with things like this. So you can visualize the weights of a simple neural network, let's say one that's trained to recognize handwritten digits. And this is a really bad one. As you can see, the accuracy is quite low for MNIST because it's a one-layer neural network. But what's really interesting about this is that we see that for each of these neurons that are responsible for they're responsible for classifying each of these digits, that if you realize the weights, it's getting an impression of what the class looks like. So we see kind of zeros and ones and twos and threes, 4, 5, 6, 7, 8, 9, the impression of these things emerging, and it does so through the process of training. That's really interesting because what we understand about neural networks, in particular with respect to images, is that they're learning how to represent a class of objects. And they're doing so without us telling them what these digits mean or what they are. And so in some sense, we can kind of think of them as we're learning a little bit about the way we perceive the world by training these neural networks, the kind of components that are the visible components that are important to understand what the sort of salient properties of a particular data set are. And this is kind of a hint of things to come, because we'll see this kind of ramped up as we look at convolutional neural networks. So really quickly, and I don't want to belabor this because I know probably lots of you have seen diagrams like this. This is kind of inspired by some work done by Jason Yosinski et al. They made a really nice toolbox for visualizing convolutional neural networks, and this is kind of doing more or less the same thing. If you look at Deep Visualization Toolbox, they do lots of other things in this vein. But basically, like, what's happening here, right? So this is what we're looking at is a convolutional neural network, which is constantly analyzing my webcam stream, and it's doing so in the following way. So at the first layer, we have this set of 96 filters, and these are all feature detectors, and this is what they're looking for. Some of them are looking for, like, let's say, diagonal lines, or yellow to green gradients, or sort of like reddish pink textures. And what we do is we slide these filters across the image to look for where in the image these features appear. And these are their individual responses. So you see that this one right here is looking for sort of vertical lines. Over here, we might be seeing more like clusters of horizontal lines, maybe more consistent gradients. All of these are basically the feature detectors, and we see the presence, the presence or the lack of these features emerging within these responses. Now, what's really interesting about convolutional neural networks is that as we stack these feature detectors on top of each other, we acquire a progressively higher level representation of the thing. So, for example, after we go into the next convolutional layer, what we've done is we've taken those responses together, and now we're applying more feature detectors upon those responses. So kind of feature detectors upon feature detectors. So at the first layer, they might have been looking for groups of pixel patterns, right? So like vertical lines or gradients or things of that sort. But at the second layer, we can combine, let's say, the horizontal feature detectors with the vertical feature detectors and detect corners. So a somewhat higher level feature detector. And as we do this repeatedly, let's say go through a process of 5 convolutions, the actual filters become necessarily much more abstract. And I really like to, I often forget where this is, but one of these I think is lighting up for my face. I've already forgotten where it is. I'm not going to find it right now, I think. Maybe this one? I forget. One of these is particularly good at finding faces. I don't think it's this one. Anyhow, some of the first research to look into this, what neural networks are seeing, and we'll see that in the next slide, was done by Rob Zeiler and Matt Fergus. Oh, I think I'm missing those slides, sorry. We'll get back to those in a second. Let me actually first introduce you to what we do, what we use this for. So then at the very last layer, we'll have a fully connected layer and the classification. So now we have over here, this is the second to last layer, and it's provided us sort of a compact representation of the image, which is kind of resistant to superficial changes in color temperature or lighting or things like that. It's really kind of looking for content. And then we attach a classifier at the end of it. So if I put my phone in front of it, you'll see it goes iPod. Yeah, so screen, CRT screen, cache machine. iPod is pretty good when I hold the phone right there. It's pretty confident about iPod. I think if I put a bottle next to it, spray. Water bottle, okay. So it's a little finicky, but it does a pretty decent job, and it does it pretty fast too. So we see that these things have really made it much easier for us to do pretty accurate classification out of the box. So, so what can we do with these compact feature representations? Well, classification is one thing that we just looked at, but really what's interesting is that these neural networks are able to give us a representation of the object. So for example, if I have a huge image set, let's say of all of these animals, I can use these encodings that we saw in the last slide, the sort of second to last layer that represents the object, and then I'm able to find the most similar images to it. So for example, this duck, or goose, we are able to retrieve very similar images. And a lot of them are, what's interesting is if you look at, for example, like the fourth one, it's very different in terms of the color and sort of more superficial characteristics, but it's able to find the same content. So we see that these, rather than looking for things that look superficially the same because maybe they have the same pixel color distribution, they're able to find content for us. So we can look for giraffes, and obviously, like maybe a dog gets mixed in there, trilobites, and we can actually drag this around and get some more visually similar images, centipedes, I guess. Lots of really interesting things we can find here, and it gives us a way of understanding our data sets in an unsupervised way, and that can be useful in and of itself. Triceratops, I like this. We find some elephants in there. So it's not always perfect, but it does a pretty decent job of giving us sort of semantically similar objects. Okay, so another thing you can do with this representation is t-SNE, is visually organizing your data set. And what you're looking at was just an animation of a t-SNE trained on 3D color points, which are color-coded, kind of giving us a 2D layout for visually similar colors. Which is kind of a trick that I like to use to visualize these things. t-SNE, of course, was initially created by Lawrence van der Maten under Jeff Hinton a couple of years ago at the University of Toronto, and it basically is a dimensionality reduction technique, which is particularly good for visualization purposes. So we know that we can use things like PCA or sound mapping and things like that to reduce the dimensionality of things, but t-SNE is particularly good at giving us really pretty ones, let's say, so to speak, because they're able to sort of preserve local structure in the graph, but maybe at the expense of a really good global perspective, but it makes it particularly good for visualization. So if we take those encodings of the images, we can visualize them according to t-SNE. We run those 4096-bit vectors from the second to last layer of the CovNet, and in order to organize these images on the 2D grid, like the following. So we go into this and we see that it's clustered together. All these sort of the owls are here, the frogs. We go to a different neighborhood. There's our sort of chimpanzee section. Marine life, so whales and sharks. Ducks and so on. You see that again, like as we saw with the last slide, it's particularly effective at grouping things by content, irrespective of the particular colors or again superficial characteristics in our data set. We can also do this with text, and I'm actually going to exit the slides real quickly and take you to, there's a page you can see on my website where what I've done is I've taken a whole bunch of Wikipedia articles that you can find from Wikipedia article on political ideologies, and I have then analyzed them using natural language processing techniques to extract the TF-IDF vectors. That's term frequency inverse document frequency. It basically measures the importance or the frequency of all of the unique terms within all of the unique articles. And that's a way of giving us an effective feature vector for each of these Wikipedia articles. And then we use t-SNE again to analyze it and graph it in 2D. So what it does is it groups, again, semantically similar or or articles that have similar content together. So we see up here, there's a sort of feminism cluster, and I think over here there's a totalitarianism, stateless communism, sort of, there's a nationalism cluster here. I think if we go to the right, there's a cluster of Christianity articles. So this is, if you're like me and you like to browse Wikipedia late at night, this is a nice way to kind of browse it. So like if you go to the, you can click into this and get the different Wikipedia articles that have been grouped together. So this is kind of a neat way of browsing Wikipedia and understanding text in an unsupervised way. Last but not least, we can also do it with audio. So here I've taken a drum sample library, and we've analyzed it using typical music signal processing analysis, measuring what are called the MFCCs of these audio samples, and then using t-SNE to reduce the dimensionality to 2 so that we can plot it, and we can kind of go around this neighborhood and listen to all the samples. So we have like a kind of a kick drum cluster here. This is pretty neat, like nice little thing that we can do with audio, and I expect to see features like this popping up in audio production software in the near future, because it helps us understand your sample library. So if you're a musician and you have lots and lots of sounds, you might want a more effective way of navigating them and understanding what's inside your collection. So I would guess that this kind of stuff that you'll start to see in professional audio production software in the near future. You can grid t-SNE assignments. So this is the same images that we saw a couple slides ago of our animals that have been that we've taken the 2D layout and actually put it into a grid. So this is just one more step, and just kind of makes a more organized way of visualizing these. And again, you see that the images have been grouped by content similarity. This is one that was made by Golan Levin and a student of his, Aman Tawari. Golan Levin is a media artist, a well-known media artist, and what they did was they took the entire catalog of IKEA and they t-SNE'd that. So you see the cups are down here, and there's like couches and cribs. There's a little crib section, drawers, picture frames, glasses, and so on. And this, to me, I don't know about you, but I think this is kind of how IKEA should organize itself if I were them. Okay, so let's start to get to the really interesting stuff. So as I mentioned briefly, Rob Zeiler and Matt Fergus first did this in 2013, where they analyzed, they did experiments which would show what each of the neurons inside of convolutional neural networks were looking at. So for example, if you these are actually basically samples, image patches, which maximally activate certain neurons. So if you see this little cluster over here of what are sort of grid-like, these are actual images, and these are image patches which seem to be correlated. So these are like sort of lattices, or almost like a honeycomb lattice shape. And this is a particular feature detector which is really good at finding these kinds of images. And at a higher layer, maybe I think this is the third layer, it might even be finding things like people or torsos, or maybe clothing or something like that. It's not always obvious. Some of these are sort of less interpretable than others, like this one in the corner. I'm not really sure what's going on here. I kind of see like cylinders maybe. But regardless, we can see what it's doing. The neurons are able to find the sort of high-level features, and they're able to do so through the process of training, discovering what those features should be. And that's really, really interesting. So what can we do, just to start to get to the more hallucinatory stuff? Everyone, well, not everyone, but probably, if you're really interested in machine learning, you probably saw last year the Inceptionism and Deep Dream work coming from Google. There's 3 engineers at Google, Alex Bordvincev, Chris Olah, and Mike Tyka, who first demonstrated this sort of Deep Dream technique. So the idea is, now what we can do is we can try to synthesize images which maximally activate certain patches. So here we're looking at real images which maximally activate certain neurons, but they probably don't, they're not necessarily perfect. what we want to do is kind of turn the problem on its head. What is a synthetic image which will maximally activate a particular region of a neural network or a particular neuron? So for example, like this image right here, the banana, this is the image that, or a image, which when synthesized and passed through a convolutional neural network, makes it think this is bananas. So, so you could see lots of sort of banana-like features saturating the image. My favorite is the parachute one, because if you look closely at it, it looks like there's a person in there. And that's pretty interesting because, you know, if you're Google's image search neural networks, right, and you get lots of pictures of parachutes, they tend to have people attached to them. So the poor hapless neural network begins to think that people are sort of a component of parachutes. Screws, obviously, you can see the screw-like features. And this was just a year ago, or a little bit more than a year ago now. I think in June 2015 that this came out. And just a year later, some work by these guys, Nguyen, Dosvitsky, Yosinski, Brax, and Klun, who used a type of technique called deep generator networks. And I'm going to get to those in just a few slides, which are really, really approaching uncanny valley territory. So you can see, like, these are fake images that maximally activate these particular classifications using a type of architecture that was not used by Deep Dream. Mosques and lipstick and bramblings, and you see, like, it's really incredible. Candles, table lamps, toasters, almost uncanny valley. And this is a year's worth of difference between this and this. So I think these things are really, really kind of progressing at light speed, and who knows, maybe they'll be almost photorealistic within some amount of time. I can only imagine. I don't know. It's hard to predict. Okay, so then we understand now what we need to know to understand what Deep Dream was. So Deep Dream was this technique where they would start with the images, actual images, and then they would evolve the pixels so as to amplify whatever activations the network thought it found. So if you pass this image of these hartebeests through a neural network, it might have, you know, a particular set of low-level feature detector activations. So like the gradients and the edges and the corners and things that we saw in the demo. What the Deep Dream technique would do was it would adjust the pixels of the image so as to enhance those activation responses, to make them bigger. So whatever gradients and edges and corners that it found, it would make them even bigger by adjusting the pixels. So that was the sort of Deep Dream technique in a nutshell. It produced lots of really cool psychedelic images that were splattered all over the internet last June. For my part, I was really taken aback by this. You know, I'd not really seen neural networks producing incredible imagery like that before, and so I started experimenting with it. This is an actual photograph of a place that's very dear to my heart, called Jaga, and passed through Deep Dream. It looks like this. And you see the correspondence from the original image, and then all of these sort of capsules and the famous puppy slugs, and you know, lots of sort of psychedelic imagery emerging, and just a few more rounds of it, enhancing different layers and so on, making some really incredible imagery. This is a sketch by Leonardo da Vinci, and this is one of my favorites, because if you pass it through Deep Dream, boom, there's the puppy slugs standing on the steps, sort of birds on top of these capsules and so on. Pretty psychedelic and pretty unreal, if you ask me, and really had a lot of fun with this. You can also make a video with it. So this is a technique that was sort of introduced by Mike Tyka, who was one of the people who worked on Deep Dream. And what he would do is he would take an image of noise initially, and then Deep Dream it, and then crop it a bit, kind of zoom in, and then Deep Dream it again, and then crop it again, and kind of recursively keep on zooming in on the resulting image, generating these sort of endless fractal-like Deep Dream space junk. Is the only way I can really describe it. I don't know. After a year, I still can't really describe it in a cogent way. I did lots of different experiments. Like you know, there was sort of, you know, the Deep Dream aesthetic was really hard to escape. You know, the puppy slugs and capsules and so on. But you could try to, for example, like make videos by kind of oscillating which of the layers. You can try to enhance the low layers of the network with Deep Stream or try to enhance the high layers. And if you kind of oscillate between the two, you can get pretty interesting looking images. Lots of other people, Mario Klingemann in particular, experimented with training his own, because Deep Stream, most people use the models that were provided by Google, but you could train your own network and use that instead. And that's something that if you look up some of Mario Klingemann's work, he was really, really keen to do that as well. And I got pretty tired of Deep Stream. As I said, the aesthetic was really, sort of, it was always there, and I started kind of seeing it everywhere in my coffee and in my food, and I kind of got tired of it last July. And shortly thereafter, the style transfer was a technique which emerged, and I had a lot of fun with this one as well. So style transfer is this technique where we recompose the images in the style of other images. I'm going to start to hurry up because I'm running a bit late. I have lots of other things to show you. So apologies if I go through this stuff a little quickly. It's all online, so it's all on my website. But yeah, in style transfer, we kind of recomposed one image in the style of another. It came from this paper, A Neural Algorithm of Artistic Style, popularized just a year ago, actually, still only about a year ago, so really new. And style transfer works by basically evolving an image so that it matches its activations, matches in content the content image, and matches in style, and I put style in scare quotation marks, in the style of another image. And I don't have enough time to really go into the math. The paper is actually quite a good explanation of it. But basically, this is kind of a view of it. So if you pass the style image and the output image through the network and look at the activations, they seem to have a similar texture to them. And that's kind of the way I understood style transfer. And that's basically what it's trying to do. And you can see it evolving over time. I'll just show you kind of a little gallery of images that I applied to it. I just took the most iconic image I could find of the Mona Lisa and applying different styles to it. So Hokusai and Tarsila's heads, and Roy Lichtenstein, Wu Guangzhou. And it's amazing, really. It seems to work on pretty much any scale. Whatever you feed into it, Crab Nebula, Egyptian hieroglyphs, Google Maps, this one I had some fun with, and the Rosetta Stone, TV broadcast signal noise. You can also just use style. So like if you don't care about the content at all, you can just produce Google Maps junk. Or and you can also make videos. So here it was a sort of naive approach. You could just take each of the frames and individually apply style transfer to it. This is Gustav Klimt being applied to Mr. Dib's disco ball, and making really cool imagery. I applied it to a video from Alice in Wonderland. If you go to my Vimeo, you can look up Why is a Raven Like a Writing Desk, where I used 17 different painting styles, really having a lot of fun to this. But again, using kind of a naive approach. So here, each frame is being style transferred individually, but really a more, if you want to produce video, a much technique emerged actually just a few months ago. I'm going to show you some stills from that. So a new technique introduced by these guys, Ruder et al., introduced a new loss term into the style transfer formula, which penalized optical flow loss. So here, this is a video I took from the J train. I used to live in Brooklyn, and different painting styles being applied to it. And you can see this new technique has much more consistency frame to frame. And so it's much better for video. Pretty interesting technique, really, really robust, and had lots of fun. Very expensive computationally. I really always keep coming back to this Google Maps texture, which is, I love because the markers here become the windows in the buildings. And my favorite one is the next one, which was Jean-Michel Basquiat, who's a graffiti artist and a painter who was quite active in New York in the 1980s. And I like to think maybe this is the Lower East Side where he lived. This is maybe a little bit what it would look like, in his imagination, so to speak. Okay, so again, going a little quickly through generative models. Generative models are a type of class of neural networks which produce images at the other end. So deep convolutional generative adversarial networks, which are made by these guys, Radford Metz and Sumit Chintala. And I had a lot of fun with these. This is just, again, some stills from their original research. So DC GANs are really interesting because you can basically play with this generative space. So it gives you this compact, latent, this sort of latent variable, 100-dimensional or 1,000-dimensional or whatever, what have you, which lets you control the generative properties of these images. In their case, they used faces. And you could perform arithmetic in this generative space, so you can kind of take the smile off of people and so on. This is really, really interesting research, and kind of a big, really looking forward to what emerges out of this. Again, some really, really bizarre looking faces that they produced. I applied it to, I was really interested in working with like handwritten digits and characters. So I started working with MNIST. So here, this is like literally interpolating the number classes. So DC GANs, because of this latent variables, this sort of latent space, we're able to get this smooth, sort of a smooth generative space that we can kind of navigate through. So these frames are kind of taken as you go between the classes. So if you go between the 3 and the 4, you kind of find the smooth interpolation between them. And it's pretty interesting, really, really, really powerful models. And this is a project I did called A Book from the Sky. Again, I really don't have enough time to talk about it so much, but A Book from the Sky was a project that explored these latent variable properties in the context of Chinese handwritten characters. This is a project I did with a friend of mine named Francis Tseng, who gave me a lot of insights into really interesting properties of the Chinese language. Because you can do things like, okay, so if you do these interpolations between different characters, that's interesting. And you can kind of see the smooth morphing between different character classes. But what's interesting is when, in the context of Chinese characters are characterized by radicals. So they're the sort of root characters which from which all of the characters derive, and I've highlighted them in red. And what's really interesting is that sometimes in these interpolations, the radicals persist through the entire. They kind of persist through the interpolations, and I kind of cherry pick. They don't always do that, but these are two examples where they happen to be particularly good at doing that. Okay, deep generator networks. This is really recent. Again, I mentioned these a little earlier. This is by Nguyen et al. Using an architecture which is very similar to DC GANs. You can read in their paper synthesizing the preferred outputs. I think convolutional neural networks, and again, uncanny valley territory. You know, telephones and table lamps. Really, really looking realistic. So I started experimenting with this. First thing I did was I actually threw it into a t-SNE. So if you organize them by the input activation codes, that may not make sense to you, but if you read the paper, it will. That goes into making these, you kind of get a sort of semantic, the digital watch and digital clock are put together, and you see, really, really realistic oscilloscope, soap dispenser, go to this corner over here, trailer truck, minivan, Jeep, garbage truck, let's see here, mosque, jack-o'-lantern, pizza. So really, really interesting stuff. I applied it to a new data set. So I found a cafe model. You need a cafe model. So you can do this in any cafe model, find one with images. Places 365, this is sort of the updated Places data set. And you can see a lot of really, really interesting, really realistic looking things. General store, glaciers. I made a few categories of them. So these are buttes. I like the way these came out. So if we have a lot of these in the US, kind of out in the West, really beautiful kind of geological formations. And here the neural network is hallucinating them. So it's quite interesting. This is one of my favorites. So if you generate boathouses, the network is actually quite good at memorizing sort of reflections in the water. So you see that the boathouse, it remembers to make reflections inside of the water, and pretty good ones too. It even matches. But in some cases, like this one, the reflections appear to be not the same. Actually, this one I think got confused. So the reflections are not the same as what is actually here. So pretty neat properties of these things. People as artifacts. So these are all different classes that tend to have people in them, and the people are quite ugly. This one looks like a certain presidential candidate that we have here in the U.S. I don't know. I like to think of who will remain unnamed. conference center, nursing homes. So you see the floral kind of pattern that I guess elderly people tend to wear in their clothing. Discotheques, so you see the crazy colors and lights. And what's interesting is we can actually watch these emerge. So it's an iterative process, and it converges upon what appears to be, in this case, we can watch it, jostle violently through this generative space until it emerges on this cheeseburger. Okay, so WaveNets, I'm gonna skip this. Unfortunately, I just don't have enough time, but WaveNets is some really recent research from DeepMind that came out where they're now generating really compelling audio samples, actually. And this was, for me, coming from a music background, this is maybe the most interesting, and I really want to experiment with this. There is an implementation that I'm working with now in TensorFlow that I've been contributing to a little bit, and really effectively makes samples, and not just actually of vocals, but even of music. So like if you listen to this, it's trained on piano samples. So right now, this is too early, just from a few weeks ago. There's not much to say about it, so I'm going to kind of gloss over it. So I don't have enough time, so I'm just going to skip recurrent neural networks. Again, a lot of this I'm going to describe to where you can find more of this stuff. But again, we saw lots of LSTMs, composing music, dense captioning, which is captioning images, which I applied to video. You can see this is the Boston Dynamics Atlas robot video that came out last year, the dense captioning. White and blue motorcycle, bike in a rack. It never calls it a machine or a robot, which is kind of the most interesting thing. Yeah, this is also dense captioning Deep Dream. So it sees dogs everywhere. Who was surprised by that? But unfortunately, I just don't have enough time. Okay, so really quickly, like what happens when these things are deployed in real time? We can use Wekinator, which is a really awesome software for playing with machine learning in the real-time context for performance reasons. And this is something you should look up online, Wekinator. And Cubist Mirror is kind of my real-time style transfer implementation. So you see this is kind of applying the Cubist style on me. And we can also switch really quickly into Kandinsky mode. Hello, everybody. I hope you're having fun watching this. Unfortunately, I don't have enough time to describe this, but it's all, again, online. Okay, so now in my last 3 minutes, I just want to quickly tell you about some resources you can use to get more into this if you so are interested into it. I teach a lot of classes, so you're looking at highlights from a class I taught at ITP at NYU last year about machine learning. It was called Machine Learning for Artists. And I put all of it online. So all of the lectures and things are accessible online on a website called ml4a.github.io. I'm going to take you through it real quick. So this is an in-progress book about machine learning for artists, which is going to be hopefully in early next year, which should be ready. Has chapters which try to describe how these things go. I publish all my class lectures on here online, so I've had 2 of them, and there are some more upcoming. So you can see that they're all sort of broken out by notes. You can go into them, and they're in segments, and you can watch them. So it's basically a really long version of this talk. We also have practical materials. So these are different guides that you can look at. They're IPython notebooks for doing things like the reverse image search that we looked at, that you can go through and really kind of learn about this stuff in much more detail. And other components to it, we're also where are we? We're also on Twitter, so that's ml4a_. And there's going to be a book also, which is in progress. And it's really not ready to go yet, but Neural Networks chapter is kind of the most complete. And it's exactly what I described. It's a book that describes this stuff in more accessible terms. It's also being translated, so there's a Chinese version and ones with a few more languages in progress. And the last thing I'll describe is AltAI. There's a conference that I helped organize last year. We had a really great exhibition and a bunch of amazing speakers, different machine learning artistic hacks, and so on. And all of that is online. So I'm basically about out of time. Unfortunately, I had to rush through a bunch of things. But if any of this stuff is interesting, you can all find it online. I mentioned AltAI. You can see some of this stuff on my website, genekogan.com. I'm also on Twitter and lots of other things. As I mentioned, I share this stuff as I go. And ml4a.github.io is what I just showed. Also on Twitter. We have lots of amazing content on there, and I'm hoping that it reaches a state of maturity sometime early next year. We're looking for contributors. So if this is the kind of thing that interests you, please get in touch with me, email me, or find me on Twitter. And yeah, keep up with it. So thank you very much for having me. I hope you enjoy the rest of the conference.